Hello, my name is Christina Thomas, and I am the Marketing Manager for Bison. I'd like to welcome everybody to the webinar, Mastering Airflow, Engineering Smarter Air Moving Systems. Today's session will help you understand blower technologies, compare brushed versus brushless blowers, and learn how to optimize performance, efficiency, and noise. Now, I'd like to introduce today's presenter, Dave Gill. Dave is a senior motor design engineer at Bison and Amatec Business. He has decades of experience developing blower systems and supporting engineers across a wide range of applications. Dave brings a practical, engineering-focused perspective to today's topic, and we're excited to have him walk us through the key considerations in designing efficient air-moving systems. Of course, we'd love to hear from you too. So if you have a question at any time during today's presentation, click the Q&A icon at the top of the screen. Type your question in the query box and click the Ask button. Dave will go over as many questions as possible at the end of the session. A recorded version of this webinar will be emailed to you within 24 hours, and the presentation slides will be in your inbox within 48 hours. And with that, I'm going to hand it over to Dave.
Thank you, Christina, and thank you to all of our guests for tuning in this afternoon. I hope you'll find this presentation valuable. Our topic is moving air and how to do it. Design engineers are often faced with the need to move air. Many applications, floor care, material transport, ventilation, fume evacuation, pressure spraying, paint spraying, to grooming animals, rely on moving air. The engineer is faced with a bewildering variety of options in blower technologies and designs to select the right one for their project to balance features, performance, size, reliability, and cost. So our mission today is to review how the engineer can better understand airflow and narrow down the choices to find optimal solutions. We will review the common technologies and their pros and cons. Although we will mention some other options, we will concentrate on brushed series universal motors and how they just might be what you're looking for. Note that access to this slide deck and other material will be distributed after the webinar, as Christina indicated, for easy reference and for access to the QR codes in the program. First, who are we? Bison is a business of Amatec, and Amatec is a leading global provider of industrial technology and solutions, serving a diverse niche markets with annual sales exceeding $7 billion. Bison was formed from combining Amatec Dynamic Fluid Solutions, formerly known as Lam Electric for many years, and Bison Gear and Engineering Corporation in 2023. For more than 100 years, Bison has been an industry leader, designing and manufacturing the highest quality fluid moving and mechanical drive solutions tailored for many applications. Our trusted brands, they're not bland, they're brands, include Lam vacuum motors, Windjammer brushless blowers, Nautilair combustion blowers, Prestolite motors, brushed DC motors, Rotron regenerative blowers, Rotron transportation pumps and motors, and the Bison lines of fractional and integral horsepower electric motors, gear motors, and reducers, and washdown motors. Bison specializes in bringing our design expertise in diverse applications to customer projects and to tailor solutions for unique needs and help to seamlessly integrate them. Our markets include combustion, medical, floor care, heavy-duty vehicle, agriculture, construction, energy, food and beverage, transportation, and many others. In air moving, we are leaders in both brushed and brushless technologies. Well, now that you know who we are, a quick tutorial on moving air is in order. First, I would highly recommend to you the white paper on the Bison website called Selecting the Right Blower by Understanding Airflow, written by Earl Clausen, one of our veteran engineers here. This will be distributed to you in the materials after the webinar. Our blowers use centrifugal fans. Air enters axially at the center of the fan, and the rotating fan blades accelerate it in a tangential direction, creating a net airflow from the fan eye to the periphery of the fan where it exits at a much higher speed. This net flow creates a pressure differential across the fan, and this pressure can be used to do work, transporting dirt from a floor to a container, moving a fluid like paint or a material like plastic pellets, or just moving air to remove fumes or to dry your dog. To quantify the properties of the airflow, we need a few definitions and units. Aerodynamic performance is the measure of the movement of a volume of air or other gas at a level of static pressure. In common English units, airflow is typically in CFM, cubic feet per minute. Pressure is in inches water gauge or pounds per square inch. If you speak metric, airflow is typically liters per second or cubic meters per hour. Pressure is millimeters of water lift or millibars or pascals, etc. Air density is very important because air performance parameters vary with the density of the air, which is a function of temperature, barometric pressure, and humidity. Performance is always corrected to standard density. So if you look at our data sheets, it's corrected to standard density, which is 0.075 pounds per cubic feet. And that translates to a barometric pressure of 29.92 inches of mercury and a temperature of 68 Fahrenheit and a relative humidity of 50%, although the relative humidity is much less important to the calculations than the first two. Now, fans and blowers have corresponding performance curves. These curves plot the static pressure on the y-axis versus the airflow on the x. So the curve shows the performance all the way from the fully open flow conditions to the fully sealed or blocked conditions. Different blowers have different performance curves, as shown in this diagram. This diagram shows three different performance curves. When air or another fluid moves through a system, any resistance in the airstream will tend to oppose the flow. To overcome this resistance or impedance, air movers need to have enough power to force the air through the system. Therefore, the fan or blower must be able to generate enough static pressure to move the air. In the photo below, what happens is you change the size of the hole in the toothpaste tube, i.e., you change the impedance. You need to vary your pressure. You need more or less pressure to get a particular flow of material. As the toothpaste example showed, for a given tube opening or impedance, there will be a curve showing how much pressure on the y-axis is needed to squeeze out a given flow of toothpaste on the x-axis. And this is called a system impedance curve. And this curve defines how much pressure loss or drop will occur as a function of how much air moves through it. Think of an electrical analog with current and voltage and impedance being resistance. So if you think about that relationship. Back to our toothpaste example again. If you were to plot an impedance curve for various size holes in the nozzle of your tube, you would get a family of curves like these. Commonly in aerodynamic curve plotting, we call these orifice diameters or effective orifice sizes. Typically, they're quadratic relationships or x squared relationships. The air performance of a blower is plotted with pressure on the vertical axis and airflow on the horizontal. In selecting a blower, the designer needs to determine an operating point. This is based on the impedance of the housing that the blower works in. It includes the airflow rate required for the application, along with the resistance to flow that the system will impose. When a flow curve is plotted with the impedance curve, the intersection defines an operating point. From this, an appropriate motor blower can be determined. One final observation on blowers and impedance. This graph shows several different impedance curves, perhaps for different systems, perhaps for the same system with modifications. There are also performance curves for two similar blowers, similar size and power level, but say different numbers of fan stages. As far as which blower is right, it depends heavily on the impedance of the system in question. It also depends on the application, which will influence the impedance at the operating point. So to choose the right blower, you need to understand your system. Estimating impedance of a system is complex. Not only the inlet and outlet areas determine the value, it's also affected by bends, passages, path length, and other parameters. Often you can get a good idea of the impedance by using a blower with a known performance. Bison blowers have technical bulletins with typical performance for an array of orifice diameters, which are basically impedances. So here are the orifice diameters, okay, which are the different impedances, and then here are the aerodynamic performance uh, parameters. Now, if you can measure the input current at the approximate operating point and look it up on the data table in the bulletin, that points to the operating orifice, and it tells you what the aerodynamic performance parameters are. In this case, you measure 11 amps. That points you here to the 0.875 diameter orifice, where you can read the performance parameters across this way: 59.6 inches, 75.1 CFM. So that's where that blower would be operating. Or you can play with the curves if you're more graphically inclined. This is the current versus flow curve, and you go to your 11 amp point, you drop down to your pressure flow curve here, and then you can read off the, the pressure and the airflow. So if you're a table person or if you're a graphic person, we got you covered. Now, to meet a customer's requirement for performance, the fan system designer has many design options to work with. First, of course, there is the motor which drives the fan system. Its basic speed torque curve can be tailored, and we'll talk about motors next. But beyond that, there are many static and dynamic elements in the fan system to tune the performance. For instance, you have the fan speed, the fan diameter, the number of stages, number of blades, shape and contour and layout geometry of the blades, the inlet and outlet angles of the blades, the blade height, and then the stationary elements like fan interstages and diffusers to help recover pressure, reduce noise, and improve efficiency. So now that we've discussed airflow and fans, let's talk about motors. What is a motor? A motor is an energy conversion device that turns electrical energy into mechanical energy. You take energy out of the wall or out of a battery and you turn it into moving air or a moving shaft, which you use to move air. Motors work on the principle of magnetic attraction using permanent magnets and or electromagnets running current through copper coils wound around iron cores, creating interacting magnetic fields, which create torque. But the magic comes in knowing where, when, how much, and how long to run current through these windings to produce and control the motion that you desire. And you do this by using switches. The difference between brushed and brushless motors designs is the kind and complexity of the switching. Once you can define the performance requirements of the blower, you can begin to answer the question, brushed or brushless. This is a fundamental question to steer your search into one of two different universes of products. So let's explore the question in some depth. First, brush motors. Brush motors use a switching mechanism that is called a commutator and brushes. Commutators are made of insulated copper bars connected to windings in the rotor or armature via hooks on the bars. Here you can see the hooks on the bars of these commutators. Brushes are conductive elements, usually carbon, that carry current while sliding along the face of the commutator and sequentially contacting the bars, and therefore switching the current in the coils of the armature. And that creates the shifting magnetic field in the armature, where and when it is needed to produce the torque. The other element of the brush motor is the field, or the stator, which also has coils wound on iron, setting up a stationary opposing magnetic field that alternately attracts or repels the armature's magnetic fields. Some brush motors use stators with permanent magnets that do the same thing. A quick look at a sectioned brush vacuum motor shows the principal parts discussed. Okay, this big copper thing in the middle is your commutator, and these guys out here, these are the brush mechanisms where you hide the carbons and load them with a spring to keep them in contact with the commutator. Here you can see the body of the armature, the iron, and you can see the copper here and here. Here's the stator or the field. This is the core. These are the field windings. Okay, and the field windings connect to the outside world, the battery the or the wall, and the other side of the field coil attaches to the brushes. So that's how a series universal brush motor goes together. Now, a brushless motor. If you are with me so far, I will bet that you figured out that brushless motors don't have brushes. The stator has windings on iron, much like the stator of a brush motor does. The rotor has permanent magnets. So here are the magnets around the inside of this cup. In this photo, the rotor is outside of the stator. The rotor cup goes over the stator. Some designs use rotors inside of stators. The switching of the windings is accomplished by electronics. Instead of a commutator and brushes, we use electronics. The switching element is a transistor called a MOSFET or an IGBT, and it is controlled by circuits on a printed circuit board. Now, a brushed motor's air performance is typically limited to the line on the graph. Okay, at a given voltage, you will get a certain airflow curve with a given fan system. In a brushless blower, because you have an electronic control, you very often have speed control built in, which then allows you to not only hit the points on the line, but also about any point underneath the line. So you have, this whole universe of performance points available to you. Well, both technologies have pluses and minuses. So let's do a brief, review of brush motors. They have a high starting torque, which is good. You don't need any additional outside elements to help get them started, like a capacitor. Um, they have a high ratio of output power to weight, which is good because that's efficient on material cost. There are a wide range of performance and application geometries available, um, which we will talk about later in the program. Switching via a commutator and brushes is relatively cheap. Brushes are consumable though, and they have a limited life. Um, they erode as the motor runs, and eventually they wear out. But life ranges anywhere from 500 to 3,000 hours, depending on the power level in the application. And finally, electronic speed controls like triac circuits tend to reduce brush life. The brushes just don't like them all the time. Now, brushless motors, uh, what are their trade-offs? Well, long life is a very positive thing. There's no consumables. There's no brushes to wear out. Uh, in our brushless motors, we typically advertise 20 to 50,000 hours of service life. Many have a 0 to 10 volt speed control input that you can either adjust the speed with an onboard or a remote potentiometer or with software. It can be set to spec in the plant if you have a specific value you want. Many have a tachometer for speed RPM output signal, which you can use for feedback. So speed control can either be open or closed loop. They have dedicated controllers or microprocessor chips on their PCBs that allow for custom software to meet specific needs. Commutation and control relies, though, on electronics, and it is significantly more costly than brush motors, depending on complexity and features. And working with brushless blowers requires a higher level of technical sophistication to design, to build, and to use. So there's a value proposition here. Brushless motors, the question is whether the advantages of brushless motors, long life, precision, controllability, are worth the significant cost upside of brushless versus a well-designed brushed system, which offers performance, reliability, and quality at a significantly lower cost than brushless. In some cases, brushed motors can offer higher air performance and efficiency, and the ability to achieve this in a smaller package. The product designer has to balance performance, features, size, life, and cost. Now, Bison provides a wide range of solutions in both brushed and brushless technologies. So, if you come to us with your problems, we can give you possible solutions in both universes. Now, before we move on to our deeper dive into brushed universal motors, let's take a look at the types of air-moving motor platforms that we typically see in applications, both brushed and brushless. Well, heat is the enemy of reliability in any device, so proper cooling is key. Cooling airflow is required to protect the motor windings and extend the life of all the motor's components. There are two constructions that are called through flow and bypass that are defined by how the motor is cooled. And a product designer trying to make a selection must understand the principles of both. In a through flow motor, the air that does the work also does the cooling. It's a simpler mechanical design, but it also presents a challenge in that the air which must cool the windings is preheated by passing through the fan system and heating up. Uh, all of that banging around of air molecules that goes on in the fan system heats up those molecules. Many applications, oh, I'm sorry. Luckily, this is partially offset by the high airflow or CFM typically seen in working air. The problem comes when the working air is restricted either by design or by a change in the operating conditions, like filters clogging up and reducing that cooling flow. Many applications and regulatory agencies require through-flow motors to have some sort of thermal protection on board to protect the appliance and/or the motor by tripping when overheated. Alternatively, the designer may choose to have the motor cooled by a separate air path. This is called a bypass motor because the working air bypasses the electrical side. The working air is separated from the cooling air. The cooling flow is provided by a separate onboard fan driven by the shaft. This may be required by the operating point, or the working air may have contaminants like moisture that can cause shock hazard if introduced into the electrical side of the motor. Bypasses also have some inherent advantages in keeping commutators, brushes, and/or electronics cooler than through flows, especially at restricted flows. Now, if you're working with a bypass motor, as a designer, you must pay particular attention to the bypass cooling scheme in your design. The working air must be kept separate from the cooling flow. So here's your working air and here's your cooling flow. You need to keep those separate. The working air is at a much higher pressure uh, than the cooling flow, and it can disrupt that flow and keep it from doing its job. The cooling path must also keep the cooling air intake separate from the cooling air exhaust. Failure to do so results in recirculation, so that as the air moves through the windings and exits, it picks up heat. And if you recirculate it, it'll go around and pick up more heat and more heat. And as one of my former colleagues said, you get the China syndrome. The motor will just keep overheating, and it can cause uh, premature failure. Now, Bison's oldest and best known products are those in our Lamb line of brushed vacuum motors. These are systems suitable for vacuum or pressure applications and based on series universal brush motors. They come in both through flow and bypass designs. These motors are designed to run equally well on AC or DC power at a given voltage, hence the name universal. Performance varies with voltage, but not with frequency. If you work with induction motors, you know that they're very sensitive to frequency, but universal motors don't really care much. Um, but we do care about voltage. But we can customize your performance for the voltage that you plan to use. And our lamp designs range from 12 volts up to 240 volts. Now, a through-flow Lamb motor looks typically like this. This is a classic design. You have the air that enters into the fan eye. It goes through the first fan stage, through a stationary element, through a second stage, and then it's guided upward between the armature and the field and exits to the ambient air. Okay. Very simple path. Now, the bypass motor typically has two different working air configurations. And remember, the key to bypass motors is they have a separate cooling fan where you have a cooling flow. But here we're talking about the working air. The one on the right, the air enters the fan eye, goes through the fan stages, and then exits around the fan casing through a series of slots or louvers. This is called a peripheral discharge. It is useful when the fan discharge does not need to do specific work. An exit to ambient is appropriate. In the other configuration, air again enters through the fan eye, goes through the various fan stages, and it exits out tangentially through a tube, which is an exhaust tube, or we call it a horn, uh, tangential to the fan casing. And this is called a tangential discharge, very original name. It is useful when the pressurized exhaust is needed to do work. That way you can guide it and put that pressurized air where you want it. Or if the designer just wants to specifically duct the exhaust air away. For instance, if you're familiar with central vacuums, you will often see that the installer will guide that air to exit outside the house. Note that bypass motors are also designed to handle clean, filtered air. I mean, no, no rocks or dirt or cats or small children are supposed to go through those fan systems. Uh, but they can tolerate moist vapor, moist air in the fan system. They are bypass motors. The working air is separate, so the top is not exposed to that moist air. Now, we do offer an alternative to traditional through flows. As mentioned, traditional through flows cool with working air preheated by the fan, and this can lead to overheating if you're operating near a blocked inlet condition, which decreases the reliability and life of the motor and requires thermal protection, which adds cost to the motor and or may require you to put bleed holes in your system to allow additional air through the motor, but that can decrease performance and increase noise. Bison has developed the reverse air motor, or the RAM as we call it. The motor side draws ambient air inward around across the motor. You notice that the fan here is reversed. Your fan eye is down here and you're drawing the motor. I'm sorry, you're drawing the working air in across, but it's ambient temperature when you draw it in. So you're cooling the motor with ambient air, and then it exits through the fan system. Now, it you still need a little bit of airflow for these things to cool. It's not free, but you can, because the air is so much cooler, you can deal with a lot less CFM and still run reliably. With RAM, the commutator and brush life and reliability are all increased compared to traditional through-flow motors. This is due to materials operating at significantly cooler temperatures. Thermal protection may not be required for RAM motors. It'll depend on the application. The RAM advantage can be used in several different ways. You can use it to increase your performance. You can drive the current up higher and get more performance out of the motor without heating it up as much. You can optimize the cost of your active material, so get the performance you want uh, with less copper and steel, or you may be able to operate at more restrictive conditions if you have an application where you want to do suction through a very small orifice. Now, the RAM technology is not limited to just a straight air exit like we showed you on the previous slide. The exit can be designed to exit peripherally, or it can turn the corner and it can exit axially. Um, Lots of choices are possible there. At this point, our best advice is if you're interested in learning more about RAM, contact us at Bison. We'd be love to talk to you about it. Now, a motor produces torque at a given speed, and that is used to drive fans. The mechanical power of the shaft imparts power to the airflow, and it does it proportionally. And this is the key relationship here. The motor output power is proportional to the speed times the torque. Okay. Now, if you look at that equation, you can obtain the same power to move air with a higher torque and a lower speed, or a lower torque and a higher speed. Okay, you gotta let that sink in a little bit. Now, torque is proportional to material requirements of a motor. So some design considerations. At a lower speed, you generally have lower noise, and higher speed, you have higher noise. So there's a strike against going to higher speeds. But higher torque requires more copper and steel. It requires larger fans, housings, etc., and more cost in general. So if you have a torquey requirement, then you'll probably pay more for it. So you need to balance these considerations. Now, to accommodate a wider range of speeds, torques, and power levels, Bison has developed a comprehensive set of lamination core sizes to create optimal solutions for design challenges. These are all lamination sizes that we have in production. Uh, well, if you're coming to us for a project, how do we pick which which lamination set we want to use? Well, it depends on how much power you need to handle. Is this a low power application or a high power application? What's your thermal condition? Is it in danger of running hot because there's not much airflow? And that determines how much copper wire we need in order to keep the thing cool. There's only so much room for wire in these little these little armature slots. Is there a specific torque requirement for your application beyond uh, beyond moving air? You know, if you've got an air moving design, but you also need to drive something off of it. For instance, think of an upright vacuum cleaner. And finally, how much room do you have? Do you have room for a big torquey motor, or do you need something smaller that'll give you the same air performance in a smaller package? So we consider all of these aspects. Now, this little chart up in the corner is just showing you what the power handling range of our various lamination platforms are. And my only point in showing you this is that, there is a lot of overlap between the various lamination platforms. So that if you come to us with a project and you say, I need to be able to do 1,000 watts, we can do it for you with our 3-inch or with our Galaxy or with our World Lam, depending on what your other requirements are. So this gives us a lot of flexibility to help you. Now, over the past 30 years, the floor care industry saw a steady downsizing of its products. At Bison, we led this trend with our smaller lamination sizes and parallel developments of components to ensure long life and durability at these smaller and faster sizes. Bearings are typically speed rated, and our limiting speeds increased from around 25,000 to well over 50,000 RPM. Internal construction was improved. We used nylon ball cages. They're lighter, don't corrode, and we've used improved greases. The commutator in brushes is another critical area for reliability. The brush is a wear item by design, so we have improved our carbon grades. We have additives for lubrication and scrubbing and quenching of sparking to improve life. Bison also developed and patented the curved Eternity brush used in several of our product lines, enabling a longer carbon to be fit into a smaller diameter housing and producing life of 1,200 to 3,000 hours, depending on the power level. Commutators must withstand centrifugal forces while running at high temperatures and speeds over 50,000 RPM. We've improved the internal anchor constructions, used reinforcing rings, and better phenolics to help hold these comms together. And of course, the fans themselves have to hold up, and we've improved those assemblies by strengthening our rivet assemblies and using better alloys of aluminum. But the key to speed lies in more than just buying good components. Bison manufacturing and quality are world class, and there are key processes in making durable universal motors. Commutator fusing and turning are crucial. Special attention is paid to varnish impregnation to help stabilize the windings. And all finished motors are given a run-in period to begin to seat the brushes and to film the commutator for reduced sparking. Finished motors are tested 100% at the end of the line for electrical and air performance and vibration before packing. Since there are a variety of brushed vacuum motors available, we have currently more than 1,400 unique Bison universal blower models. There are questions you should consider to determine the ideal design for your application. And these are all listed here. Okay, what type of air will you be handling? Do you have to handle dry air or moist air? What are your cooling requirements? Do you need a bypass? Can you get by with the through flow? Will thermal protection be required? Is that to protect the motor or to protect your enclosure? What is your air operating point? What airflow pressure or suction is permissible? Or what is your permissible current draw at those values? Or what input power will be necessary to perform your intended job? Do you have mounting and interface requirements? What is the voltage? AC or DC? Line voltage or batteries or some other power supply? What other features do you need? Thermal protection, serviceable brushes, specific air inlet or discharge, bearing protection, specific life requirements? Do you have regulatory agency requirements, specific insulation class needs, thermal protection for locked rotor in unattended installations, end product agency requirements such as blocked inlet protection? We are familiar with many UL end product standards, and a number of these tests we can do internally to help you in your development. For the many options we have discussed here, here's an overview of available diameters, stages, and discharges of Lamb motors. The web links down at the bottom allow you to get more details on the available motors with what their voltage, power levels, and basic air performance are. And they also have links to our technical bulletin sheets for the models. So we have bypass platforms here. We have diameters from 4.8 to 9 inches, and our number of stages vary considerably. In through flows, we're limited to 1 or 2 stages, sizes from 4.2 to 5.7 inches. We also recommend to you this white paper about Lamb Series Universal Motors, which is also on the Bison website and which I believe is also among the materials that Christina will be making available to you. So before we move on to your questions, we hope that we have given you some insight in how to use Bison air moving products in your application, that you have a better idea of the brush versus brushless question, that you have been introduced to the variety of platforms, sizes, and design features in our Lamb Series Universal product lines, that you can find what you need in our catalog offerings, or better still, come to us with your project and let us help you succeed. And finally, that you come to us with questions for recommendations or to partner with us for something unique to your needs. Okay, with that, I will return you to Christina.
Thank you, Dave. Before we jump into the Q&A, let's quickly review what attendees can expect after today's event. Within 24 hours, all attendees will receive the webinar recording via email. Within 48 hours, all attendees will receive the presentation slides with active links to additional resources, including the 2 white papers, Selecting the Right Blower by Understanding Airflow and Not Your Grandfather's Universal Motors Anymore. So you can either scan those QR codes now for immediate access or click the links when you receive the slides. We'll give you a few seconds here for those who wish to scan those codes. We'd also like to invite you to charge ahead with Bison by harnessing our herd strengths for your next project. You can win in the marketplace. But since proof speaks louder than promises, we're sharing a collection of case studies. These stories show how companies across diverse markets and applications collaborated with Bison and won in the marketplace. So again, you can either scan the QR code now for immediate access or click the link when you get the slides. Now, let's charge ahead with the live Q&A session. Are you ready, Dave?
I'm as ready as I'm going to be.
Okay, great. The first question is, how do I determine the optimal operating point if my system has variable impedance across use cases?
Well, there's no simple way of doing it. Depends on depends on how important it is that you meet those points exactly, in which case you probably want some sort of a speed control system. Or you can figure out where your most important operating point is and design your system there.
Right? Okay, and just a reminder, if you'd like to ask a question, you can click the Q&A icon at the top of the screen. You can type your question into the query box and then click the Ask button. I do have a couple more questions here for you, Dave. How do brushed motors hold up in high-duty cycle environments compared to brushless options?
Well, they hold up very well. We do life testing here in our facilities, and we can change the cycle time on life testing, and it we don't see a degradation in life due to uh, rapid cycling. So uh, they hold up very well.
Okay. Can you share examples of how Bison customizes blower specs for niche OEM applications?
Let's see. One that comes to mind is we've done a series of motors for people in the pressure paint sprayer markets. Uh, they came to us with a design uh, criterion. They had a class of blowers that they call HVLP, high pressure, low volume, which paradoxically, given our normal universe of performance, is more like uh, no, it's high volume, low pressure. I'm sorry. It's paradoxical for us because for us, they're high pressure, low volume. So regardless, we designed a series of motors for them over the years with the additional fan stages, with 4, 5, even 6 fan stages, because as you add stages, you add pressure. And so we have been able to supply those specialized motors to those markets. And that is a niche. Uh, Most people don't need that kind of pressure for their applications.
Okay, great. How do lamb motors perform in environments with high particulate exposure or moisture?
Um, Exposure, uh, if it's, we like to see the working air filtered, and we say that in our application notes is for clean filtered air. Um, as far as moisture is concerned, we uh, uh, we have specialized over the last 50 or more years in doing bearing protection systems, ways of trying to protect the bearing from the effects of moist air or moist air with detergents in them. It was originally done for the floor cleaning market where you have uh, floor extractors that you're putting down and sucking up detergent laden water. And this water dumps into a reservoir, but the air's damp. It's moist. There's suds in the air, and we've been able to come up with protection schemes. And over the years, I mean, I think our first patent on those was in the late 1970s, and we continued to improve that protection uh, to the point where our 6.6 and 8.4-inch bypass universal motors are are extremely durable in the field in these high moisture applications.
Right, I have another question for you. What's the typical life cycle or maintenance interval for brush blowers in industrial settings?
Well, that's kind of hard to answer in general. Different platforms have different life expectancies. Like I mentioned, the 6.6 and 8.4 designs with the curved brushes, those uh, those are well over 1,000 to 2,000 hours, uh, possibly more in low voltage applications. Uh, More typical vac motors that you would see in an industrial setting are more like 500 or 600 hours. Uh, they typically have replaceable brushes, either the cartridges or if you can buy just the carbons and replace those yourself. And again, it depends on your application, how many hours a day you run it, and which motors that you're using.
Okay. Next question is, are there specific failure modes more common in through flow versus bypass configurations?
Um, Through flow, not necessarily. In both of them, the most common failure is just brush wear out, and we're in at similar power levels. You get similar hours for through flow and bypass, but it does depend on your airflow. If you've got an application that tends to run at a small orifice, it'll run hotter, and that can cause premature brush failure. Uh, it can cause bearing failures. You can, if it runs hot, you can cause your grease to eventually evaporate and the bearings to fail. Uh, you can see some of that in bypass motors, but they tend to run a bit cooler on the motor side because of the extra cooling. But then the bypass motors are often exposed to moisture, and if you don't have bearing protection in the design you're using, then that can be a problem.
Okay. Next question is, what's the best way to balance airflow performance with energy efficiency in a compact design?
Hmm. Well, through the years, we have improved the efficiency of our fan systems. Our most well, our most efficient through flows are our 5.7-inch, what we call our Advantech series. Uh, in the bypass motors, our most efficient platforms are the 6.6 and 8.4. They're somewhat bigger, uh, but they also have, we use better steel in them, a little more efficient there. Our fan systems have really good efficiency, so those motors are in the uh, in the low 40s in terms of overall if a fan motor fan efficiency in the low 40s compared to some of our older designs which are in the low 30s.
Okay. Next question is, what are the most effective ways to reduce noise without sacrificing airflow?
Noise is a perennial problem. It's not an easy one to solve. We have done some fan systems here that are relatively quiet, but a lot of times it's easier to try to treat it in the area outside of the motor uh, by using by using foam around the housings, by putting some additional bends in to make the path of the noise a bit more tortuous, things like that. But it's a constant problem that we face with our customers is how to try to reduce that.
Okay. Couple more questions. How do you approach blower selection when the system has tight thermal constraints?
Well, we need to understand what your constraints are, and we would try to maximize the amount of copper that we have in the motor. The larger the copper you have in the design, the less resistivity you have. You get less I squared R losses, so that keeps the temperature down. Uh, we sometimes would need to try to do something to guide the air better. If it's a motor that we can improve baffling on or something like that, so that the CFM that you do have are going where they make do the most good. Things like that. We need to know what your constraints are and what your product is like and how we can customize the motor to work best that way.
Okay. And we probably have one more question. What are the trade-offs when selecting a blower for battery-powered systems?
Well, you really need to look for efficiency uh, because efficiency you are trying to get a certain level of performance with the least amount of current draw that is possible. Okay, because if you use less amps, you get, your amp hours get more hours, if that makes sense. Uh, so if we can make the motor more efficient so it draws less current and still gives you the performance that you need, then that should improve your battery life. And again, our more recent designs, our 6.6 and 8.4 low voltage versions are quite good at this.
All right, great. Thank you so much, Dave. And that's all
You're
we have
welcome.
time for today. Thanks for attending our webinar. If you'd like to charge ahead with Bison, please visit us at info.bisonamatech.com/charge ahead. Thanks, everybody.